In this lecture, we are going to be introducing electrostatic equations, in particular one called the Poisson equation, and then we'll go over boundary conditions, where for the first time we will talk about materials that meet together and what kind of rules apply in those situations. So we have three parts into this lecture. The first is the Poisson equation, second is electrostatic boundary conditions, and finally we will go over some examples. So let's start out with the Poisson equation. Now let's take a step back for a second and review kind of what we've done so far in electrostatics. And we've really only talked about three things. The first, we have this idea of electric charge, which is sort of the ultimate source of everything. It's the ultimately where electricity comes from. But from electric charge, we basically had two other quantities that emerged from it. The first is called electric field lines. Or we also have electric flux lines, flux density lines. These were closely connected. And these were also basically, they emanate from charge or they fall into charges. We have this notion that charges are the ultimate source of field lines. But field lines can exist anywhere, and they describe the ways in which charge can interact via force with other charges that are somewhere else. And these were vector defined, that anywhere in three-dimensional space, I can walk around and I can define at that location a field line that has a direction and a length to it that tells us something about what is the force on a charge at a given location. But through all this, we have just finished by introducing what we call electric potential. Potential was a way of describing the fact that anytime we have multiple charges that are exerting forces on each other, we've got potential energy that's built up, much as if I take my pen and I raise it up, because of the force of gravity between the earth and my pen, when I raise up the pen, I'm giving it potential energy because I could let go and it would fall downwards. And the same thing will have to exist with electric charges. And we talked about how we build up electric potential. Now, we have a number of laws that are basically going to relate these to each other. For example, to go from field lines to electric potential, we can apply a line integral. So for example, the integral of the electric field dotted with some path dl will be equal to the difference in the electric potential between point A and point B, where A and B is basically the beginning and the end of some path that you're taking, some line integral. We can also connect potential with field and flux with a microscopic definition called gradient. Basically, that the electric field equals the negative gradient of the electric potential, where the potential is simply a number like temperature defined anywhere in space. The electric field would be the direction of the fastest decrease in that potential energy level, since it tends to pull charges in such a way as to decrease their energy, much as gravity pulls my pen downwards. And that negative sign accounts for that fact that it's dragging things to lower energy levels. We also have two relationships in between field, flux, and charge, and those were both called Gauss's law, but we had two different forms of Gauss's law. One was the integral form, which told us that if we integrate across the outside edge of some object, some closed object, right, like a sphere or a triangle or a pyramid, any three-dimensional shape, if we integrate around the outside of that object, the electric flux density dotted with a small vector passing through the outside of that boundary, that would simply be equal to the total of all of the charges contained within that object. And this was called Gauss's law. But Gauss's law also had another form, a differential form, which looked like this. It was the divergence of the electric flux density equals rho v. These are mathematically equivalent, but the latter was a little bit more powerful. In divergence, we describe as the sourciness, or the degree to which field lines emerge from a given location. And it's negative, that would mean field lines are converging into a given location. Now we're missing something here. Obviously, we'd like to have some links between potential and charge. And today we're going to introduce one of them, and that's what the Poisson equation is. Now, if you want to get from potential to charge, you might quickly guess that you want to go from potential to field and then from field to charge. And that would be a pretty good guess, and that's exactly what we're going to do. So we're going to put together the definition of electric potential with Gauss's law, and we're going to combine those to derive what we call the Poisson equation. So let's take a look at this. All right, let's start out with Gauss's law in differential form, that the divergence of the electric flux density, or grad dot D or del dot D, equals rho V, the charge density. But we have another relationship that we can include here, the fact that the electric flux density equals some permittivity times the electric field. And so we can substitute that in. The divergence of the permittivity times the electric field equals rho V. I'll just write that right there so it's cleaner. And now let's simplify this a little bit by assuming that epsilon is a constant. We have one homogeneous material, and it's just a number like 5 anywhere. And so we're going to pull that out. And when we do that, we're going to get this. It's just epsilon times the divergence of E equals rho V. But we're not done yet, because we also have a second definition of electric field that basically connects it to the electric potential. And that is that E equals the negative gradient of electric potential. Let's substitute that in. And so we have epsilon times grad dot grad V. I'll pull out the negative sign, equals rho V. And let's just finish this off. So we have the divergence of the gradient of the electric potential equals negative rho V over epsilon. All right. Now the gradient and the divergence, right? These are two different ways to define the spatial derivative of a function in 3 dimensions. And we're actually combining them. And so what we're going to have here is basically a second derivative. In fact, this idea, the divergence of the gradient, is powerful enough that it gets its own name, and this is called the scalar Laplacian. And so it gets its own notation, which is going to be grad squared of V. And if you work it out, you actually apply the definition of divergence and gradient. It works out to be the following: the second derivative of the potential with respect to x plus the second derivative of potential with respect to y plus the second derivative of potential with respect to z. And the Poisson equation tells us that that's strictly equal to negative charge density over epsilon. So again, this is called the Poisson equation. Now, what does it mean for us to have a second derivative of the voltage? Right, so think about what the shape of the voltage could be. If the voltage is a straight line, right, a ramp, or a road that's going straight, that would imply that there is no second derivative. If we have curvature to this, then there is going to be a second derivative. So for example, this would be an upward curvature. And this would imply that there is a positive second derivative. And alternatively, we could have a declining curvature like this. This would be a negative second derivative. So qualitatively speaking, Poisson's equation is pretty simple. It tells us if there's a net second derivative, there's got to be charge there. Right? So this idea of kind of like a rising curvature, a second derivative, this indicates that there must be negative charge kind of scattered throughout where this curvature is. This declining curve, the second derivative, implies that there is positive charge probably scattered along this shape right here. Right? This negative sign flips things around. So a positive second derivative means there must be negative charge. So to put this in words, we can basically say that positive charges are like mountaintops. And negative charges are like valleys, where things bottom out. Right? And that's basically all that Poisson's equation tells us, but it does that in 3 dimensions, right? And it does it microscopically. That doesn't mean anytime there's positive charge, you must have a mountaintop, but there's sort of a mountaintop-like element to it, right? So you could have something that looks like this, right? This curve right here has a negative second derivative. So there are positive charges here, even though this never actually reaches a mountaintop, but there still must be positive charge scattered throughout this section right here, because again, it has a negative going second derivative, so that implies positive charge. And so there are a couple of sort of unique advantages to the Poisson equation that make it practically very useful. The first is that unlike Gauss's law, it relates a scalar to a scalar. So electric potential or voltage is something that's relatively easy to measure with certain instruments. Electric charge is not, and electric field is not so easy either. And so this seems to be the best way that we might connect something easily measurable to something that's not, in particular to charge. So if you've got some box and you have the ability to measure the electric potential at lots of spaces within that box, we have a straightforward way to link that immediately into charge. And by the way, from charge, you can also get electric field. The second advantage the second of 3 advantages is that because it's a scalar, we have less things to keep track of. If I want to go into this box and measure the electric field everywhere so I can apply Gauss's law, then I've got to keep track of 3 components of the electric field at every single location, and that's a lot. The voltage, on the other hand, is just 1 quantity at every location. So there's less to keep track of. It's easier in that regard. The third advantage, or the other advantage, has to do with the fact that we're dealing with second derivatives instead of first derivatives. And let me describe now how when we set up a numerical approximation, it's actually going to simplify the problem greatly compared to what we had to deal with a Gauss's law type solver. All right, so I'm going to describe to you something called a Poisson solver. And these are actually commercial products you can go out and buy or pay for that will directly link a set of electric potential measurements with where are the electric charges. And here's basically how they work. They're basically going to divide up space into little pieces. And to show that, I'm going to go ahead and draw a 4x4 grid in 2 dimensions. Unfortunately, I can't do this in 3 dimensions on this little screen here, but you can generalize this to 3 dimensions and hopefully you'll get the idea. And inside of these cells, I'm going to draw variables V representing the measurements of voltage or electric potential in every single one of these grids. And I'm going to put a number below this to indicate basically the X and Y cell number. And so this would be V11, and this would be V21, since we sort of stepped 1 in the positive X direction. This would be 3,1 and 4,1. Again, that's kind of like the X and Y component. And we can just keep this going. This is 1, 2, 2, 2, 3, 2, and 4, 2. And bear with me as I finish this off. 1, 3, 1, 4, 2, 3, 3, 3, 4, 3, 4, 4, 3, 4, and last but not least 2, 4. All right. So given all this, can we approximate the second derivative? And let's just do one example. So let's say we want to figure out what the second derivative of voltage is with respect to X, and we wanted to define that at 0.33. Right, so we're defining it right here where I'm going to put this red dot. Now let's apply our definition of the first derivative that we came up with earlier, which is that you go on either side of it, and then you take the difference between those two, and you divide it by the delta X between them. So I'm just going to remind you, we have a definition of delta X, which is basically the separation between these cells. And we can do the same thing for delta Y. And so the approximation of the second derivative can be thought of as take the first derivative and look at the difference from one side to the other. So this is going to be equal to dv dx evaluated at point a half a grid cell in the positive x direction from 3, 3. So it's basically going to be, hang on a second, 3.5 and 3, right? Because we're going to go in the positive direction by a half a grid cell, and we're going to subtract that from the same measurement, but 1/2 grid cell in the other direction. So it's going to be minus dv 2.5, 3 with respect to x. Right, so these two measurements are basically taken on either side. I'm going to draw a green dot here and a blue dot. And so here's the blue and here's the green. Right, the green dot is basically the derivative defined where this blue dot is, and the blue, sorry, that's the green, and the blue term is basically defined over here. I actually switched those. So let me correct that real quickly. Switch the blue and the green. The green is defined here, and the blue is defined there. All right. And we got to divide that by the difference or the horizontal separation between those two cells, which is delta x. Right. Now, to take this one step farther, we can approximate the derivative again, right? We can approximate this first derivative. And that's going to solve a big problem for us, because when it came to a numerical solution for Gauss's law, we had this issue where the green dot and the blue dot are not aligned with the same grid that the red dot is. And we had to sort of average multiple different derivatives to sort of account for that. And as you're about to see, we don't have to do that here. And that's a huge help. All right, so let me just start by, let's approximate this dv 3.53 dx. All right, this is going to be equal to v at, I'm going to take 3.5 and I'm going to add a half a grid cell to it in the x direction. So this is v defined at 4, 3, minus v defined at, I'm going to take 3.5 and I'm going to subtract a half a cell. So it's v defined as 3, 3, and divide that by, again, a delta x. This represents our approximation of that first blue term. Right? We just approximated the approximation to get the second derivative. And let's do the same thing for the second term, for the green term, minus v 3, 3 minus v 2, 3 divided by delta x. This is our approximation for the second term. And then that whole thing, we've still got to divide that by the delta x. Right? That was this delta x kind of remaining present. Now here we can simplify things because we got this delta x's that we can combine. We also have the v33 repeating twice. So we take this minus sign, distribute it, and combine these terms. It works out to be the following. It's v43 minus 2 v33 plus v23 divided by delta x squared. So this is our approximation for d squared v dx squared. And notice immediately that unlike the Gauss's law numerical approximation, all of these points are right on our grid. V33 is right here, V43, V23, those are actual cell points where we already have defined our voltage. And so we can now define the second derivative of the voltage in the same places that we define the voltage itself. We don't have a misalignment of the grids, which means that we also are going to define the charge in the same places where we are defining the voltage, and that's a tremendous help. We can repeat the same process for the second derivative with respect to y and the second derivative with respect to z, and all we got to do is combine those, and we have our answer, right? We've got our grad squared of v equals negative rho v epsilon, right? So that's the building block. We can approximate the second derivative basically using the cells that immediately are adjacent. So if we want to approximate the second derivative at the red dot, v33, we need the 2 points on either side of it, v43 and v23. We need the 2 points that are above and below it, v34 and v32. And we also need this in 3 dimensions, the point that it's above it out of the page and above it below the page in that angle. If we take the measurement at all those points, we can approximate the second derivative. And we're done, right? And once we have that second derivative, we know exactly what the charge density is from the Poisson equation. Now, there's one little problem here, which is that what do we do when we are calculating this for one of the cells that's at the edge? All right, so for V41, we're going to need to know what the voltage is at this point right here, right? This point that is basically outside of our measurement space. And we can't have a measurement space that goes on forever. At some point, a measurement space has to end, and we have to calculate a solution there. And so Poisson solvers basically need to be seeded with an assumption about the boundaries of this object. And it's very common to start out with the assumption that around our measurement space, we have a potential of 0. Once you seed it with that, a Poisson solver is basically going to calculate the voltage for every single other point within this and give you the answer of what the charge is. It can also go in reverse, by the way, and figure out what the voltage is if you know where the charges are. The latter is a little more complicated. You have to set up a matrix equation, but it is doable. But going from voltage to charge is relatively straightforward. You just need to calculate the second derivatives, and that is your approximation for the charge. So this sort of powerful technique, again, is called a Poisson solver. And it is used to solve real-world problems, given the ease of doing it. But this should give you a hint that there's something interesting coming that we're going to have to handle, which is boundaries, right? Because I mentioned two things. The first is I got to have something that defines what the conditions are outside this object. But we also made an assumption that this object was just a single material. It's all air, or it's all water, or it's all silicon. And of course, in the real world, we're going to have much more complicated problems than that. And so what we're going to need is a way to deal with this problem, even if that's not the case. Even if all of these cells that I'm now shading, if all of these shells are, say, metal, all these cells are metal, then how can we solve this same problem? In order for that to happen, we're going to have to introduce a new set of constraints, a new set of equations, in order for this to be solvable, in order for us to be able to figure out all those unknowns, the charge density in each grid cell. And in the next video, we're going to actually figure out what those constraints are to complete and close this problem.